Let's now talk about radioactivity. Radioactivity tells you how many nuclear decay reactions happen over a certain period of time. And there are a lot of different units for radioactivity that are used, but the most common one that you're going to see in homework problems is units of becquerel. When you see a radioactivity value given in units of becquerel, that tells you the number of disintegrations that happen per 1 second of time. And when we take a look at this form of the units for becquerel, what we recognize is that a becquerel is essentially telling you the rate of the reaction, right? Because when we're talking about a rate, we're discussing the change in something per unit time. And here, the change is like the number of disintegrations, and the unit of time is the seconds. So you can think of becquerels as being analogous to a rate. All right, and that's going to be helpful for us in our next example when we're going to talk about how we can calculate the radioactivity or how we will calculate this decay rate. We're going to refer back to our previous example that we worked on in our last problem, where we dealt with our 20-gram sample of polonium-208 that was undergoing alpha decay with a half-life of 2.9 years. In the previous example that you saw in our last video, we found that the rate constant for this was 0.24 years to the minus 1. Additionally, we were given what the molar mass of polonium-208 was in our previous video, and we want to now find what the radioactivity of this sample is in units of becquerel. It's helpful for us to write out what the units of becquerel mean. So once again, we'll say that becquerel tells you the number of disintegration reactions. So that's going to be the number of atoms that decay per second. And again, this is just another way of expressing the rate for the process. So what we can start by doing is writing the rate law for this reaction. Now, to write the rate law, we would say rate is equal to the rate constant K times the concentration of our reactant. In this case, it's polonium-208 that's reacting. And it gets raised to the first power because remember that nuclear decay reactions always happen on first-order kinetics. So raise it to the first power. Now let's take a look at units here. So back in the kinetics chapter, we talked about how rate is generally expressed in units of molarity per second. And for a first-order reaction, the rate constant K carries units of seconds to the minus 1, and concentration is in units of molarity. So when that gets multiplied together, you end up getting molarity per second as your rate. But what if we use different units in the problem? What if instead of expressing the rate in molarity per second, we express the rate in numbers of atoms that decayed per second? So instead we could say that the rate is in number of atoms decayed per second. Well, now let's take a look at what we would need on the right-hand side of the equation. So for the right-hand side of the equation, the rate constant will still be in seconds to the minus 1. That's going to be our time unit. But instead of expressing the concentration of polonium-208 in molarity, we're going to express it in a number of atoms. Because when you do that, you're going to multiply these together to get number of atoms per second, which is the units of becquerel that we're looking for here. And so this is how we're going to find the units of becquerel. We're going to take the rate constant in seconds to the minus 1, and then we're going to multiply that by the number of polonium-208 atoms. I'm going to go ahead and move all of this up a little bit to get a little bit more space to work through this problem, and we'll just move over to another slide for that. All right, now the first thing that we're going to have to do is express the rate constants in units of seconds to the minus 1. So we're going to convert it from years to the minus 1 to seconds to the minus 1. So here's how we're going to go about doing that. We're going to start by writing our K value of 0.24, and then it's years to the minus 1, so years goes in the denominator here. Now, I don't know how many seconds there are in a year, but I can go through a series of conversions to turn years into seconds. Because I do know how many days there are in a year. I know that in 1 year, you have 365 days. Unless that year is 2020, in which case there's a million days, but we're just going to pretend that it's a normal year here. All right, so the units of years cancel out. And now we have days to the minus 1. Next, I know how many hours there are in a day. I know that in 1 day, you have 24 hours. All right, so now I've converted from days to the minus 1 to hours to the minus 1. All right, and then next, I know how many minutes there are in an hour. All right, I know that in 1 hour, there are 60 minutes. All right, so now I have units of minutes to the minus 1. And then lastly, I know how many seconds there are in a minute. I know that in 1 minute, there are 60 seconds. And so that gets me all the way to seconds to the minus 1. Now you could plug all this into your calculator and find what the rate constant is in seconds to the minus 1, and it will be 7.6 times 10 to the minus 9 seconds to the minus 1. That gives us the first part. So now we have the value of K in seconds to the minus 1. The next thing for us to do is to have the concentration of polonium-208 expressed as a number of atoms. So now we're going to convert the mass of polonium-208 into a number of atoms of polonium-208. All right, and we know how to do that, right? You can start by writing out the mass of polonium-208 that you have, 20 grams, and then we're going to convert that into moles using the molar mass of 207.98 grams per mole. Now we know the number of moles of polonium-208, and the next thing for us to do is convert it into a number of atoms by using Avogadro's number, which says that 1 mole of polonium-208 is 6.02 times 10 to the 23 atoms of polonium-208. Therefore, the number of polonium-208 atoms is 5.79 times 10 to the 22. The last thing for us to do is to multiply these two values together. Multiply the K by the mass of polonium-208. So I'm again going to move everything up a little bit and then finish this problem off. All right, now what we're going to find is that our rate expressed in units of becquerel will be the rate constant K, which is 7.6 times 10 to the minus 9 seconds to the minus 1, times the number of atoms of polonium-208, which was 5.79 times 10 to the 22 atoms. When you multiply all of that together, what you're going to get is 4.4 times 10 to the 14 disintegrations per second. And that's written as seconds to the minus 1, or you could write it as becquerel. So 4.4 times 10 to the 14 becquerel is our radioactivity for this sample. And there it is. All right, in our next video, we're going to talk about how you can use radioactivity values to do radiocarbon dating, or how to do isotope dating.